Hi everyone, I'm Joey Carlson. I'm a fourth year PhD student in the Department of Electrical and Computer Engineering at the University of California, San Diego. And today I will be presenting our work for the 2023 IEEE GLOBECOM conference titled Dynamic Metasurface Antennas for Energy Efficient MISO Communications. That's the background and motivation for dynamic metasurface antennas. Next generation wireless communication systems are looking towards larger and larger antenna arrays. Where 5G, we could be on the order of hundreds of antenna elements, and 6G could even be on the order of thousands of antenna elements. As we scale up the number of antenna elements, looking at a traditional analog precoding architecture with phased arrays here, we will also be leading to a larger hardware footprint and higher power consumption, since we will also need to scale the number of phase shifters and power amplifiers with all of these different antenna elements. Thus, to create these really large arrays for these next generation wireless communication systems, we will need a solution to reduce the hardware footprint and power consumption of our antenna array. The solution that we're proposing is the use of reconfigurable antennas within these large antenna arrays. So we can think about three different types of apertures that we could use for our antenna array. We could think of just having a static antenna, no phase shifters, which is a very simple design, but it's not dynamic. We cannot do beamforming with this if we had hundreds and thousands of these static antennas. We could look at the phase subarray, which is what we were just considering as our analog precoding architecture. But this would require our power dividers, our many phase shifters that have to go along with each element and power amplifiers. And so this, while we scale up the number of antennas, we also have to scale up all of these other different hardware components. Rather than this, we're looking towards the reconfigurable antenna architecture, where rather than controlling and doing beamforming with phase shifters, we have these reconfigurable low power components that are integrated onto each of the different antenna elements, such that we can have low power and a simple design with fewer components as we scale up the number of antennas in our antenna array. More specifically than reconfigurable antennas, we'll be looking at the use of metasurface antennas, a type of reconfigurable antenna for the use of these large antenna arrays. And so as mentioned, instead of having these phase shifters for doing beamforming, we will be replacing these phase shifters essentially with a control line to control all of the different integrated components onto the different elements. Now, the additional benefit of using a metasurface antenna here is that it is a waveguide fed architecture, so we can also reduce the number of power amplifiers and power dividers, since we'll have multiple antennas on the top of the waveguide, and so we need to excite one waveguide and have one feed for that waveguide, which will excite all of the different antenna elements. And because these reconfigurable components are going to consume minimal power, and especially minimal power compared to phase shifters, these metasurface antennas can enable low power precoding. There's been a large amount of recent work being done in the field of dynamic metasurface antennas, giving these potential power consumption benefits over digital and analog array architectures. There's been work with dynamic metasurface antennas using tunable continuous varactor diodes to steer beam patterns, and even create DMA prototypes where we can enable beamforming with this continuously tunable component for each of the DMA elements. There's also been work on essentially coded metasurface antennas, where instead of having a continuously tunable component, we have a binary component, where we can have codes for the different metasurface antenna elements to also enable things like beam steering and beamforming. Lastly, there's been more sophisticated signal processing work being done with DMAs that investigate things like maximizing spectral efficiency for uplink communications. In our proposed work, we want to build on this different prior work and investigate energy efficiency more thoroughly for dynamic metasurface antennas. So first, rather than relying on dynamic metasurface antenna models to set antenna element weights and steer beam patterns, we want to integrate a realistic DMA design, so actually designing something in electromagnetic simulation software and obtaining beam patterns, and then mixing this with a realistic channel model so that we can actually calculate spectral efficiency without having to make any assumptions about our DMA model or our beamforming weights. Moreover, we want to extend these different beam patterns to a DFT codebook and make a practical codebook of beam patterns for our designed DMA and HFSS. And then lastly, given our realistic channel model and also incorporating a power consumption and a component loss model, we will be analyzing the resulting spectral efficiency of both a DMA and comparing that to a traditional analog phased array. We will now go into more detail about the DMA operation, how we can do beamforming with DMAs, and our rate calculations. So as we've already discussed a little bit, these dynamic metasurface antennas are a type of reconfigurable slotted waveguide antenna. Our waveguide is sort of the base of this structure for the antenna, and different slots within the waveguide with this specific geometry act as the DMA elements that radiate out power from the waveguide. These reconfigurable components, as we've shown here as varactor diodes, are then integrated into each of the different DMA elements to reconfigure that radiated beam pattern. And so that reconfiguration actually works by altering the resonant frequency of each of these different DMA elements. So as we see in our varactor diode circuit model there, the varactor diode is a tunable capacitor here. So it'll have a tunable capacitive component and then a parasitic inductance and resistance. And when we tune that capacitance, we can tune the resonant frequency of the different DMA elements, which allows us to achieve different amplitude and phase values for all of the different DMA elements. And if we can tune the phase for the different elements, then we can enable beamforming, which is how that low power beamforming works for DMAs using things like varactor diodes. Now, the DMAs have significant potential benefits in terms of power consumption and low power beamforming. Naturally, this does not come without some limitations or constraints compared to the traditional analog pre-coding architectures. So first, in terms of the waveguide-fed operation of the dynamic metasurface antenna, the waveguide propagation that feeds each of the different antenna elements actually introduces an inherent phase advance and attenuation of the fields within the waveguide for all the different DMA elements. So in order to steer beam pattern in a specific direction with the DMA, we need to counteract this phase advance that gets fed to each of the different elements, and we need to make sure that we account for this attenuation of the waveguide fields within the dynamic metasurface antenna. Moreover, due to the reconfigurable components, such as the varactor diode here, the dynamic metasurface antenna has a restricted weight range or weight distribution compared to traditional analog beamforming architecture, such as with a phase shifter. So in the plot on the right, we see the ideal phase shifter model with a unit amplitude curve. Whereas for the dynamic metasurface antenna beamforming weights, we have this, what's called the Lorentzian constrained weight distribution, which involves only half of that complex plane, so the lower half of the complex plane, and a variable amplitude distribution, which means that the phases are coupled with a specific amplitude on that curve. So these beamforming weights then need to be accounted for when we're trying to steer a beam pattern with our DMA. We can now just discuss a little bit more about our approach for the rate performance evaluation. So our MISO OFDM signal model for our DMA is going to consist of an effective wireless channel where we incorporate both the actual wireless channel, which is in our case going to be a simple line of sight channel just for simplicity for our analysis. We also lump in that waveguide phase advance term into that channel as well to create an effective wireless channel for our proposed, for our MISO OFDM signal model. Then with this effective channel, we have our DMA beamforming vector, which consists of those Lorentzian constrained weights on that curve that we saw in the previous slide. Then the rest is very typical and consistent with other signal processing work, where we have our SNR, our desired symbol scent, and our noise. Then to calculate our spectral efficiency for our dynamic metasurface antenna, we'll use the equation listed on the bottom, where our beamforming vectors are going to be coming from a DMA codebook that we're going to design, which is going to be a DFT codebook. For a MISO OFDM signal model, we'll be summing the log2 term over all the different subcarriers, and so to calculate our final spectral efficiency, we'll be doing that for the codebook, for the code word within the DMA codebook that maximizes the spectral efficiency at all the different subcarrier frequencies. Now to develop this DFT codebook and get these realistic code words for our DMA codebook, we'll be using a design DMA based on the work in the reference listed below, which operates at 15 gigahertz, and we have 5 different DMAs with 8 elements each placed side by side to create and steer different beam patterns in HFSS. Here we show how our DMA DFT codebook compares with a traditional phased array DFT codebook consisting of different patch antenna elements. So given our restricted weight distribution for our DMA elements, as shown on the right, we can steer a beam in different directions by actually mapping our desired weight on our unit amplitude curve onto the Lorentzian constrained distribution, as shown there on the right. And now in prior work, there has been multiple different proposed methods to do this mapping onto the from the desired weight onto our Lorentzian constrained distribution. And 2 of them are shown here, which are denoted as the Euclidean and the Lorentzian mapping. But both of these different methods allow us to steer a beam pattern with a DMA as long as we know those unit amplitude phased array weights. Now looking at our specific DFT codebooks and how the beam patterns look when we steer in the various directions. As expected, our phased array DFT codebook has very nicely shaped beam patterns that steer in the right directions with minimal error in the steering direction. While as for the DMA, the steering direction is a little more variable. There's a bit more error there, and the beam widths all vary between each other, and that is due to the mapping procedure on the right, where we do not have access to the full phase range. We have a limited phase distribution and amplitude distribution. Therefore, the beam patterns are not going to look as nice and consistent as that of the patch antenna phased array in HFSS. With these DFT codebooks for the patch antenna phased array and DMA, we will now calculate some spectral and energy efficiency results with a realistic channel model. Before diving into the spectral and energy efficiency results, we show here a couple of the trade-offs between the different precoding architectures between a DMA array and the phased arrays. So for the DMA array, since the elements are electrically small compared to those of the passive and active phased arrays, we can expect there to be lower radiation efficiency in these antenna elements compared to our patch antenna elements. Moreover, as we already saw in our DFT codebook, we will have lower beam forming control compared to the phased arrays due to our Lorentzian constrained distribution. However, compared to the phased arrays, we should also have lower power consumption, which can significantly improve our energy efficiency since the varactor diodes are low power and consume negligible power compared to the phase shifters here. So for the phased array architectures, we are taking into consideration both active and passive phase shifters. For the active phase shifters, we can actually add gain into our input power, and so we are expecting lower component loss and greater beamforming control because we're using phase shifters. However, active implies power consumption. We need to consume power to control those different phase shifters, and so we're expecting to see higher power consumption in this case for the active phased array. For the passive phased array, however, we are assuming phase shifters that consume negligible power as well. So this architecture should have low power consumption with the DMA array. However, these passive phase shifters can often come with significant component loss to them, so we are expecting to have a high amount of component loss for the passive phased array. Then to calculate energy efficiency, we will be using a power consumption model based on prior work that thoroughly goes through the power consumption of many of the different components in our DMA and phased array architectures. So we have models and specific values for the phase shifters, the DAC, the local oscillator, RF chains, and the phase shifters as well. And including, in addition to power consumption, this prior work also incorporates the component loss due to these phase shifters and the power dividers. And so we can fix the input power, assume a certain input power for all the different array architectures, compute what the applied power would be to all the different antennas that includes the component losses from the power dividers and the phase shifters, and then determine the power consumed by that different hardware for all of the different components for the DMA and phased array. And then calculate the energy efficiency as the ratio of the spectral efficiency to that power consumption. Now, the most notable and important thing to note here is that while the phase shifters, specifically for the active case, will add power consumption to that total power consumption of the system, the varactors consume negligible power, so they will not be added to the total power consumption for the DMA, which we expect to see in the resulting energy efficiency as well. We now finally show here our spectral efficiency analysis for our DMA versus the phased array architectures. These simulations were done using the simulation software Quadriga, where we are creating realistic channel models using this software and then inputting our DFT codebook beam patterns into that software to calculate some resulting spectral and energy efficiency values. Now for the line of sight case, as we expect, the active phased array performs the best. It has additional gain in additional gain in the antenna due to the active phase shifters, and it has the greatest beamforming control since it is using phase shifters and not the restricted DMA weight distribution. So as expected, the active phased array does the best here, but also will consume the most power, as we'll see in the next slide. Now, on the other end, the passive phased array here actually does the worst in terms of spectral efficiency, even far below the DMA by about 7.4 dB. Now this is due to the fact that the passive phased array has a high component loss of maybe around 8 or 9 dB that we are modeling. Thus that high component loss leads to a significantly lower power applied to the antenna than the DMA and active phased array case, and can significantly reduce that spectral efficiency. Now, this is for the line of sight case. For the non-line of sight case, where there's no direct path between the transmitter and the receiver, overall we find that the spectral efficiency reduces by a significant amount as expected, and the same exact different trends apply here, where the active phased array case performs the best and the passive phased array case performs the worst. We now show results for the energy efficiency, which incorporates both the spectral efficiency in that previous slide, as well as the calculated power consumptions for both the phased array and DMA architectures. Now for the line of sight case, we see that the energy efficiency of the DMA is actually double that of the active phased array architecture at both of their peak values. Which means that even though the active phased array performed better in terms of spectral efficiency than the DMA, the additional power consumption from the active phased array and a potential component loss from the power dividers ultimately led the energy efficiency to be about halved of that from the DMA. So we're finding that in this case, the power consumption savings due to the varactor diodes for the DMA can be quite significant compared to the active phased array. Moreover, for the passive phased array, while it still ends up having a performance and energy efficiency comparable to that of a DMA, we need to put in more input power to lead to have that same energy efficiency, since the curve is shifted over to the right. And since the spectral efficiency was about 7 or 8 dB lower than the DMA, overall the DMA is by far the most energy efficient option in our analysis for the line of sight case. Now for the non-line of sight case, however, where there's no direct path between the transmitter and the receiver, it turns out that the DMA and the active phased array actually have very comparable performance. And so the DMA power consumption savings are less relevant in this case due to the higher input power and the power consumption mostly being dominated by the power amplifier at the higher input power. And so we less see those power consumption savings due to the DMA. Therefore, so the DMA outperforms both the passive and the active phased array for the line of sight case, as long as the input power is somewhat small, such that we can see the impact of the DMA power consumption savings. We discuss here some of our next work that we envision on dynamic metasurface antennas. While hybrid precoding involves the use of a digital and analog precoder to do beamforming jointly, we envision the next revolution for MIMO to involve a tri-hybrid architecture, where we have both digital, analog, and a reconfigurable antenna to do that precoding and beamforming. Thus, we can scale up the number of antennas and minimize the amount of power consumption and maximize performance by adding in this reconfigurable component at the transmitter, in addition to having the typical analog and digital signal processing. And this will be a joint precoding algorithm altogether to allow for all three of these to work to maximize that performance of our MIMO system. And more specifically, we envision DMAs to be a part of this, a key part of this, as the reconfigurable antenna. Lastly, we'll summarize our results here and talk about some of our other future work. In this work, we designed our DFT codebooks with our DMA elements, and using HFSS, we're able to calculate and evaluate the energy efficiency of a DMA compared to a typical phased array architecture, and we saw that DMAs can enable essentially twice the energy efficiency of a traditional analog phased array for the line of sight case. Sort of continuing to make the case that DMAs can enable much more energy efficient operations than traditional digital or analog precoding. In future work, we hope to extend our DMA design to have further optimization in the design and also fabricate the designs and take measurements rather than doing simulations in HFSS. And we also hope to develop more sophisticated DMA signal processing algorithms for MIMO, so working more on the DMA precoders with our restricted weight distribution, and looking at other applications like channel estimation or multi-user MIMO. Thank you so much for listening to this talk. If you have any questions and comments, please feel free to contact me at the email below. Thank you.